Good morning, students. In this lecture we are going to discuss homomorphism and isomorphism of semigroup and monoids. Okay, so first of all, the definition of homomorphism of semigroup. So definition is, let S star and T star dash be two semigroups. A function f from S to T is called an homomorphism from S star to T star dash if the following condition hold. And the condition is f of A star B is equal to f of A star dash f of B for all AB belongs to S. So this is the simple definition of homomorphism of semigroup. Here there is we use the binary operation of semigroup S, and here it is the binary operation for the semigroup T. Okay, remember it. There is so f of A star B is equal to f of A star dash f of B. That is the binary operation of S converted into the binary operation of T, that is the star dash. Okay. Now if f is a homomorphism and f is onto, okay, homomorphism plus onto, then we say that this T is homomorphic image of S. Okay. F is onto homomorphism, then the domain is said to be homomorphic image of codomain is said to be homomorphic image of domain. Okay, that is T is homomorphic image of S. T is homomorphic image of S. Okay. Now the isomorphism of semigroup. Let S star and T star dash be two semigroups. A function f from S to T is called an isomorphism from S star to T star dash if the following condition holds. What is the condition? F of A star B is equal to f of A star dash f of B for all AB belongs to S. That is same as in the homomorphism. And the second one is f is 1 1 and onto. Okay. Now we know that 1 1 and onto function is said to be bijective function. So that is f is a bijective map, or we can say that f is 1 to 1 correspondence from S to T. So if f is a isomorphism from S to T, then we say that f is homomorphism, also f is bijective, that is 1 1 and onto. Hence, if f is isomorphism, then f is homomorphism and f is a bijective. Okay. If two semigroup S star and T star dash are isomorphic, then it is denoted by S is isomorphic to T. Okay. This is we use this notation to show that S is isomorphic to T. Okay. So this is the simple definition of isomorphism. Now next, theorem number 1. If f is an isomorphism from S star to T star dash, okay, these two are semigroup, then f inverse is also an isomorphism from T star dash to S star. Okay, what we want to prove? F is an isomorphism given from S star to T star dash. Now our aim is to show that f inverse is also isomorphism from T star dash to S star. Okay. Now let us see the proof. Here f S to T is an isomorphism from S star to T star dash. It is given. So this implies that f is a bijective map from the definition, and f of A star B is equal to f of A star dash f of B for all AB belongs to S. Now since f is 1 1 and onto, and we know that inverse of function is obtained only when given function is 1 1 and onto. So here f is 1 1 and onto. So f inverse, this implies that f inverse is the map from T to S. Okay, f inverse T to S F inverse, the map from T to S exists, okay, because F is 1 1 and on 2, and F inverse is also 1 1 and on 2. It is well known, okay, because if any given function is 1 1 and on 2, then their inverse exists and it is also 1 1 and on 2. So F inverse T to S exists and it is also 1 1 and on 2. Now there is only one condition remaining, which is, now we saw that F inverse A dash star B dash is equal to F inverse A dash star F inverse B dash, okay. So now we saw that F inverse is homomorphism. The only condition 1 1 and M2 we get from here, okay. So now we will show that F inverse is homomorphism. For that, consider two elements A dash and B dash belongs to T, okay, which is the codomain of function F, okay. We have considered A dash and B dash belongs to T. Since F is onto, our map F is onto, so for A dash B dash belongs to T, we get AB belongs to S from the definition of ontoness, okay. For A dash B dash belongs to T, we get AB belongs to S, such that F of A is equal to A dash and F of B is equal to B dash. This implies that A is equal to F inverse A dash and B is equal to F inverse B dash. Simple computation, okay. Now F inverse A dash star dash B dash is equal to F inverse. Put the value of A dash is equal to F of A star dash and B dash is equal to F of B. So we get F inverse F of A star dash F of B. This is equal to F inverse F of A star B, okay. Now F inverse composed with F, composition of F and F inverse A star B. Now the composition of F and F inverse is the identity function, okay, and the identity function will get the same value, that is A star B, but the value of A is equal to F inverse A dash, so we get F inverse A dash star F inverse B dash. So what we obtained, F inverse A dash star dash B dash is equal to F inverse A dash star F inverse B dash. Hence F inverse is homomorphism and F inverse is 1 1 and 1 2, okay. So F inverse is bijective homomorphism from T to S. So F inverse is isomorphism from T star dash to S star, okay. This is the simplest explanation of this theorem, okay. There is nothing much hard in this theorem. So let us go for the next theorem, theorem number 2. Let S star and T star dash be monoids. We have considered two monoid S star and T star dash be monoids with the identity E and E dash, okay. E is the identity of S and E dash is the identity for T, okay, respectively. Let F is a map from S to T be an isomorphism. F is a given to be an isomorphism. Then our aim is to show that F of E is equal to E dash. That is, F of E is identity for T star dash, okay. So let us see. Let B be any element of T. We consider arbitrary element B belongs to T, okay. Since F is isomorphism, our map F is isomorphism, so F is 1 1 and 1 2, and F of A star B is equal to F of A star dash F of B for all AB belongs to S. Now B belongs to T and F is onto. From the definition of ontoness, for B belongs to D, there exists an element A belongs to S, such that F of A is equal to B. Now A can be written as A star E apply the function f on A. So we get f of A is equal to f of A star E. This implies f of A is equal to B is equal to. Now from the definition of homomorphism, f of A star E is equal to f of A star dash f of E. This implies that B is equal to f of M is equal to B. B is equal to B star dash f of E. Give the equation number A. Now next is similarly A can be written as E star A. Okay. This implies, now again apply the function f on this equation. So we get f of A is equal to f of E star A. This implies that f of A is equal to B is equal to f of E star dash f of A, because f is isomorphism, so it is homomorphism. This implies that B is equal to f of E star dash B. Now from the equation number A and equation number B, it is clear that for any B belongs to T, because our B is any arbitrary element of the T. For any B belongs to T, B is equal to, from the equation number A, B star dash f of E is equal to f of E star dash B. So we get this equation, that is B star dash f of E and f of E star dash B is equal to B, which means that this is the definition for the identity element, which means that f of E is an identity element for T. That but identity element of T is equal to E dash. So we get f of E is equal to E dash. This is the proof. From above theorem, it is clear that if S star and T star dash are semigroup such that S has an identity and T does not, then S star and T star dash cannot be isomorphic. શું કહેવા માગે છે કે આપણે કોઈ બે સેમિગ્રુપ કન્સિડર કરીએ. If we consider two semigroup in which first semigroup S star has an identity but T star dash does not contains identity element, that is S star is monoid but T star dash is not monoid, then S star and T star dash cannot be isomorphic. Okay. Now let us move to the next theorem. Now theorem number 3 is, let S star and T star dash be monoids with identity E and E dash respectively. Okay, E is the identity of S and E dash is the identity of T. Let F is map from S to T be an homomorphism from S star onto, here it is onto, okay, to T star dash, then f of E is equal to E dash. In last theorem 2, we have given f is isomorphism from S to T, okay. But here we have given that f is homomorphism from S to T, which is onto. In last theorem, isomorphism is given, in which f is 1 1 and onto and f is homomorphism. So we used ontoness of the function f to show that f of E is equal to E dash. And here it is also says that f is homomorphism plus f is onto. So this is your assignment to write down the proof of this theorem, okay, which is same as the proof of theorem number 2. There is just only change, f is here, f is not onto, or we are not using ontoness, here f is not 1 1 and we are not using 1 1ness of the function in the proof, okay. We are only using the ontoness of the function to show that f of E is equal to E dash. Now theorem number 4, let f be a homomorphism from a semigroup S star to semigroup T star dash. Okay, f is given to be homomorphism. if S dash is subsemigroup of S star. S dash is given to be subsemigroup of S star. Then f of S dash is equal to set of all t belongs to T, where small t is equal to f of S for some element S belongs to subsemigroup S dash. Then image of S dash. What is this? This f of S dash. This is the image of S dash under the function f. Is a subsemigroup of T star dash. Okay. We have given two semigroup S and T. S dash is given to be subsemigroup of S star, and we have given that f of S dash. It is the image of S dash under the function. Our aim is to show that f of S dash is subsemigroup of T star dash. Okay. To given any set, first of all we show that this given set is non-empty. Then after we will show that this set is closed under binary operation of star dash. Okay. Here S dash is subsemigroup of S. It is subsemigroup of S. This implies that S dash is non-empty set. Now S dash is non-empty set. This implies that the image of S dash under the function f, that is f of S dash, is also non-empty set. Okay. So f of S dash is non-empty set. Now f of S dash is equal to set of all t belongs to T, where t is equal to f of S for some S belongs to S dash. So this is the set of element from the T. Okay. So from the definition of f of S dash, it is clear that f of S dash is non-empty subset of T star dash. Okay. F of S dash is non-empty subset of T because all the element of f of S dash are from the T. Now consider any two element T1 and T2 belongs to f of S dash. These elements are from the f of S dash, and the element of the f of S dash are of the form f of S for some S belongs to S dash. So we get there exists S1 and S2 belongs to S dash such that f of S1 is equal to T1 and f of S2 is equal to T2. Okay. Now we show that T1 star dash T2 belongs to f of S dash. That is, f of S dash is closed under the operation star dash. So T1 star dash T2 is equal to f of S1 star dash f of S2. Now f is homomorphism, so it can be written as f of S1 star f of S1 star S2. So T1 star dash T2 is equal to f of S1 star S2. This is equal to f of S3, where S3 is equal to S1 star S2 belongs to S dash. As S dash is subsemigroup of S. Why this possible? Because S dash is some subsemigroup of S. So for these two elements S1 and S2, S1 star S2 also belongs to S dash because S dash is subsemigroup, so it is closed under the operation star. Okay. So S3 is also the element of S dash. So T1 star dash T2 is equal to f of S3. Now this is the form of the element in the f of S dash. Okay. The element in the f of S dash are of the form this. Okay. So T1 star dash T2 is also the element of f of S dash. So T1 star dash T2 belongs to f of S dash. This implies that f of s dash is closed under the operation star dash. Also, this implies that f of s dash is subsemigroup of T star dash. So, this is the simple that our aim is done, that is f of s dash. What we are going to show? We are want to show f of s dash is subsemigroup of T star dash. So, we are done. Now, the theorem number 5. If f is homomorphism from commutative semigroup, here we have given that semigroup A star is commutative. F is homomorphism from commutative semigroup on S star onto, also given that F is onto a semigroup T star dash. What is given? F is homomorphism from commutative semigroup S star to onto T star dash. Then T star dash is also commutative. So here is F is homomorphism from S star onto semigroup T star dash. Now our aim is to show that T star dash is commutative. So we have considered two elements of T star dash. So let us see. Let T1 and T2 be any elements of T. We have considered two elements of T. Now T is onto. Okay. Here reason is T is onto. So since T is onto, so there exists S1 and S2 belongs to S, such that f of S1 is equal to T1 and f of S2 is equal to T2. Now T1 star dash T2 is equal to f of S1 star dash f of S2. Now f is homomorphism, so it can be written as f of S1 star S2. Okay, this step can be written as f of S1 star S2. Now S star is commutative. Okay, S star is commutative. So S1 star S2 can be written as S2 star S1. So f of S1 star S2 is equal to f of S2 star S1. So again f is homomorphism, so we get f of S2 star dash f of S1. Now f of S2 is equal to T2 and f of S1 is equal to T1. So we get T2 star dash T1. Okay. So since T1 and T2 are arbitrary elements of T, okay, for these elements T1 star dash T2 is equal to T2 star dash T1. What we get? T1 star dash T2 is equal to T2 star dash T1 for all T1 T2 belongs to T. Okay. So this shows that T star is commutative. Okay. What we have given? We have given f is onto homomorphism from S to T. S is commutative. All then we say that T is also commutative. So this is our aim and this is the proof. Okay. So this is enough for this lecture. In the next lecture we are going to discuss some examples of isomorphism of semigroup. Okay. Thank you.